Hey guys, welcome back. We're going to talk about the fourth gas law. We've talked about Boyle's, Charles, and Gay-Lussac's gas law. So now we're going to talk about the fourth one, and that is the combined gas law. With the combined gas law, we're looking at the three quantities that are going to change. The temperature, the pressure, or the volume can change in this particular case. In the previous example, they were being held, one would be held constant in that scenario, but in this case, all three of them can change and will change, all right? And so the equation that we have is P1V1 over T1 is equal to P2V2 over T2. Now, when you look at this, this may look a little similar to Boyle's law right here. This part of it looks like Boyle's law divided by temperature, and that's kind of what it is, all right? But another way that we can look at this equation is to say P1V1T2 is equal to P2V2T1. I just cross multiplied. And I just brought up that T2 up here and that P1, and it's a lot easier to work with this equation than this one at times, just because you kind of see where you're going and what you need to do. All right. So let's look at this example here. I have a gas that has a volume of 3.6 liters. It has a pressure of 1.05 atm and a temperature of negative 15 degrees Celsius. What will the volume be at STP? So let's go ahead and start listing out what we do know. We know our initial pressure is 1.05 atm right here. We also know our initial volume, which is 3.6 liters. And our initial temperature, negative 15 degrees Celsius, but I added 273 to this problem to get 258. Again, must be in Kelvin in order for it to work. Now, for the final pressure, volume, and temperature, that's going to be a little, you may think it's a little tricky, but really I've given you all the information you need. It's at STP. In a previous lesson, I told you that the values for standard temperature and pressure, they're set. And so the standard pressure in this case will be 1 atm. I'm going to use 1 because I'm starting in atms, so I'm going to end in atms, okay? My final volume, that's what I'm looking for, and my final temperature is 273. It's always 273. That's the standard temperature. And so when we use this equation, P1V1T2 is equal to P2V2T1, I divide both sides by P2T1, and I get a working equation that looks like this. V2 is equal to P1V1T2 over P2T1. Okay, and so I plug in my numbers from what I've listed over here. My kelvins are going to cancel out. My atms will cancel out. I'm left with liters, which is great because I'm looking for volume, so I need my answer to be in a unit of volume. And so I plug that in and I get 3.999, but I only need two significant digits because this is the least precise number. This is 2 sig figs. This is 3 sig figs. We don't factor in temperature when we're trying to figure out significant digits, but even so, because it's in Kelvin, it's 3 sig figs, so the least precise would be the 2 sig figs. So my final answer would be 4.0 liters, okay? All right, so we have 3 problems here. That should go on the left side of your notebooks. Same thing like before, you'll have some problems. The problems will be online for you to check to see if you're going in the right direction or you have the right setup or what have you. And if you have questions, please feel free to reach out like you've been doing. All right, Dalton's law of partial pressures. This is kind of switching gears a little bit, and we're going to kind of go back to the last gas law. But it's just saying that the total pressure in a mixture of gases is going to be equal to the sum of those partial pressures. All right, so in this example here, we have a 46 ml sample of oxygen that's collected over water at 25 degrees Celsius. Now, the fact that it's over 25 degrees Celsius is not going to be important in the equation because we're not going to use it. All right, the total pressure is 102 kilopascal, and we want to know what is the pressure, the partial pressure of oxygen at STP. All right, and so the equation, as I told you before, it's the total pressure is equal to the sum of the partial pressure of the gases that's involved. We know oxygen is a gas, it told you that, and it's collected over water. In this case, it must be steam. That's where the gas would be coming from. But because we're looking for P2, I'm going to subtract the partial pressure of water from both sides. to have this equation P2 is equal to the total minus the partial pressure of water. Okay, and so we're going to plug in that information. The 102, which is our total pressure provided in the equation, minus 3.167 kilopascal. Now, I know some of you guys are wondering, where did you get that from? It's actually in your textbook. It's on page 263. There's a table with a list of partial pressures. So you will always be provided with that type of information. That's not typically something I'll ask you to calculate unless you've been given something else, okay? So just a matter of subtracting the 3.167 from the total, and my equation or my answer is 98.8 kilopascal, and that's our answer for this. All right, so here are a few more vocabulary terms or conditions that you should be familiar with, and it's talking about the gas and the mole and how it's related. So the first one is the law of combining volumes. What this is saying is that under equivalent conditions, the volume of a gas and its products are expressed in ratios of small whole numbers. So remember when we're doing stoichiometry, we're looking at the balanced equation, those numbers, those coefficients would be the mole ratio. And that's essentially what this is talking about. Gay-Lussac's law of combining volumes is dealing with that stoichiometric part of the gas laws. And so we're going to do that as well, don't worry. Avogadro's law, it's saying that a volume of gas, if it's at constant temperature and pressure, is directly proportional to the number of moles of gas. So what this is saying is that as you're increasing the volume of the gas, the number of moles will also increase. And again, that's mainly the thing that I want you guys to get from Avogadro's law. I'm probably not going to have anything else, no like equations or anything like that, but that's the main thing that I need you guys to understand the relationship, what Avogadro's law is talking about. This next one is talking about the molar volume. This is an important one. It's 22.4 liters per mole. You would kind of treat this like Avogadro's number when we talked about it in chapter 9. So it's a way to convert or go between the number of moles and the volume of that particular gas. All right, and so you would use that to convert between the two. So what this is saying is that 1 mole of gas at STP occupies 22.4 liters or 0.0224 cubic meters. Now, it's not very often that I will use that cubic meter volume. Usually it's the 22.4 liters, but I guess it's just good to know that kind of thing. Now, one of the other things I need to point out is that this is at STP. If the gas is not exhibiting standard or it's not at STP, then you don't need to use this particular number, the 22.4 liters. So that's only valid if it's at STP. All right. So let's look at an example problem here. We have a gas that is that's 4.00 moles, and it's at STP. So that's kind of my clue. First of all, it's moles, and we're at STP. So the good thing here is we're trying to figure out volume, and there's a way to do that. We set it up like we've done in the past. We have 4 moles, which is our starting point of this substance, and we're going to use the molar volume to convert between moles and liters. So our moles would cancel out here. I'm left with liters, and so I multiply 22.4 times the 4 to get 89.6 liters at STP. Now this part, the at STP, is very important. Yes, you do need to include that, because if you don't, then I don't necessarily know that it's at STP. All right, so make sure that if you have something that's at STP, because again, we're only using this number when it is at STP. If you don't tell me that, I won't know that. Okay. All right, using the molar volume and the combined gas law. So kind of both things that we've talked about in today's lesson. So the question is, what volume will 2.5 moles of hydrogen gas occupy at 300 Kelvin and 300 Kelvin and 400 torr? All right, before we can really move forward, we need to figure out what the volume is of this particular hydrogen gas. We know that it's 2.5 moles, so we're going to use the molar volume to go between moles and liters. So our moles will cancel out here. I'm left with liters, and I multiply 22.4 by the 2.5 to get 56.0 liters at STP. Now it's very important again that I say it's at STP because that also tells me information about the temperature and about the pressure. And so let's go ahead and list out what we do know, what we're starting with. Our initial pressure is going to be 760 torr. Why did I pick that? Well, because I'm ending in torr, so I'm just going to keep it in torr. All right. My initial volume is the 56. That's what we just calculated. And our initial temperature is 273 because, again, this was at STP. So that is why it's very important to know that it's at STP. All right, so our final pressure is going to be the 400 torr. Again, looking at the equation. Final volume is what we don't know. That's what we're trying to figure out. And our final temperature is 300 Kelvin. Right here. All right, and so now we're going to use the equation that we were given earlier, and we're solving for V2 just like before. So P1 V1 T2 over P2 T1, and we set that up and we plug in our numbers there. Okay, so our kelvins cancel out in this equation, or in this case, our torrs are going to cancel out. I'm left with liters, which again is great because I'm looking for a unit of volume, and that happens to work out that way. So when I plug this in, 760 times 56 times 300 divided by 273 divided by 400, I get 116.9, but I only need 3 sig figs, so I round it to 117 liters. 3 sig figs here, here, and here. All right? Okay, let's move on. I'm going to look at the comparison or using the molar volume and density. And we know that density is moles per, or grams per liter, all right? But in this particular case, because we're looking at molar volume, it's a little bit, there's a little bit of a change to it. It's the molar volume over the liter. So density is typically going to be in grams per liter, which it's provided there, all right? And the molar mass is in grams per mole. That's what we're trying to figure out. We know how to calculate molar mass when I tell you exactly what the element is, but in this particular case, you don't know that. You only know the density. All right, and then of course our molar volume is 22.4 liters per mole. So this is going to be very important to convert one thing to the next, or to get us to that answer. So we set up the problem just as we normally would. So we start with the density portion of it, 1.25 grams per liter, all right? And we're going to multiply that by the molar volume, which is 22.4 liters, okay? And so I know it says equal here, but we're going to actually multiply because that's how we're going to get rid of some things here. Our liters are going to cancel out, and my unit that I'm going to be left with is grams per mole, which is great because I'm looking for molar volume. Grams per mole is what I need. All right, and so when I plug that into the calculator, I get 28.0 grams per mole. Now the second part of that, it says what element would this be, and this includes our diatomic elements. If you were to look at your periodic tables right now, you would see that it has silicone with a 28.09 gram molar mass. But silicone is not a gas, so that would make a whole lot of sense. But because I said that it can be a diatomic element, let's go ahead and divide the 28 by 2, because I know diatomic means 2. And when I do that, I get 14. Give or take. So actually my diatomic element, or my element of unknown origin, would be nitrogen in this case, because nitrogen is 14.01. Multiply that by 2 to get 28. Okay, and that's kind of how we arrived at that. If you have any questions, please do not hesitate to ask. I'm here to help you. I will be available online for you to discuss anything that you need. All right, see you guys soon.